So, sorry about that. Just making sure we have the stream set up. Let me try and get this little window off here. Great. So today we're going to talk about simulation. So Carl-Henric introduced a lot around how we do machine learning and how we try and encode beliefs as probabilities and fit those models, in particular with Gaussian processes and what the philosophy behind that is. But one of the key sort of notions in this course is that in many of the sciences, we actually have some understanding about how the rules according to which the world operates. So we have that quote from Laplace about, which is known as Laplace's demon, that if we knew all the natural laws of the universe, the situation of all the data, and had the ability to do compute, we can just project forward. Now, across most sciences, this has sort of been the way that we make predictions. And so I just want to sort of pause and consider this work, which is The Structure of Scientific Revolutions, Thomas Kuhn. How many people have heard of this? A little bit. But you may have heard the word paradigm. So actually, Kuhn brings paradigm into popular usage. And he means it in a specific way in science, but actually it's been translated into popular usage to sort of mean the same thing across the board. And that popular usage is some way of thinking about things, you know, in some sense. Now, for Kuhn, he's looking at the sociology of science and, as the title says, the structure of scientific revolutions. And the way he thinks about that is that there are two stages to science. One is working within a paradigm, and he refers to this as puzzle solving. So a paradigm might be paradigm defining works are things like Newton's Principia. So it defines a set of laws about how the world operates, in Newton's case, gravity and acceleration and forces. And once you have those set of laws, you can work within those laws to try and make predictions, scientific predictions. Now, lots of things come out of Newton. For example, pretty much all of our understanding of fluid mechanics, Navier-Stokes equations, how we predict the weather, is actually Newtonian. I mean, it's difficult Newtonian because these are compressible fluids, but fundamentally it's Newtonian. You don't need to go beyond Newton. But then there have been things that move away from that in terms of paradigm. So you look at Einstein, and his interpretation of space-time shows that Newton's view of the way these things work collapses at sort of high energies, and you have to start using other equations. And that's what's known as a paradigm shift. A paradigm shift, I don't know whether people prefer paradigm shift. And that paradigm shift, according to Kuhn, is the other phase of science. It's where someone's realized, they think outside the box and they realize something new. And then it's a sort of massive shift in the way we think about science. And of course, in physics, there were a lot of these paradigm shifts at the sort of turn of the last century. So not only Einstein with sort of relativity, but then when Planck started looking at energies at very low levels and realized that the only way he could explain black body radiation was through modeling them as quanta. And then we start to have the emergence of an understanding of the wave-particle duality. And people start looking at quantum mechanics and realize actually at the very low scale, things don't map up well to, and we still can't bridge our understanding of gravity and quantum. So that's another paradigm shift. But what's also interesting about how Kuhn describes what's going on is what Kuhn says, and this is, I think, is in the late 60s, this is published, if I remember well, is that paradigms in his time, he felt were defined in textbooks. He sort of said there'd been a shift, that in the early days of science, when Newton writes Principia, or these other great works, these works are written, some original text from Maxwell on whatever the relevant text is on electromagnetic radiation. And these texts define the paradigm themselves, like the original piece of work. But then Kuhn says by this time, but sort of during the 19th century, so during the time of Maxwell, that somehow shifted to its textbooks. textbooks that students are reading and learning from that defines the paradigm. And you, as scientists, are taught about the paradigm, and you're mainly taught to work within the paradigm, right? It's very rare that you shift outside the paradigm. So how's that relevant for this course? Well, my argument is that this is no longer true. That today, the paradigm is more defined within computers than within books. Now, that's a provocation. It's still definitely defined within books. But the point that I'm trying to make is actually a lot of our understanding of the way we run science, as we've been able to compute more and more complex models, where is our understanding of climate embedded? It's within the climatologists for sure, but it's also within these code bases they're using, which are much harder for us to gain access to and understand. Or if we think of during the COVID pandemic, if you were following the epidemiological model predictions that people were making, you had a load of sort of epidemiologists who had these computational models of the way the pandemic was going to propagate, which not even the person that had written the code could remember everything that was in the code because it was written by them and a team. So you've got this sort of weird situation where the scientific knowledge of our current paradigm is also being pushed into the machine. And that brings great benefits because it means we're able to simulate systems that would be beyond our ability to work out analytically, right? So we can combine, we can perform numerical solutions of systems, and that's mainly what we're going to sort of talk about today, how that looks and some examples of those. But it also brings great challenges because it means that we're suddenly faced with systems that are basically impossible for one human to store within their head. And that the way we interact with these models becomes very different. So a classic model that we might look at, and I think we'll mention next time a little bit in epidemiological analysis, is known as the SEIR model. And he says that, and now I can't remember what the compartments are, but it's a differential equation model of how disease progresses with these different states of I is infected and R is recovering, or I think it also R can be dead as well. Susceptible, exposed, infected, recovered. Look at that. Yeah, it's in there somewhere. And these different states of number of people you have in each of these states, but it's a continuous differential equation. It has all these sort of weaknesses in terms of continuous differential equations of that form are actually operating in a way that well-mixed chemical fluids would operate, right? That's not how people interact. So these things are only approximations to the way diseases propagate. But the nice thing about if I have an SEIR model is a statistical epidemiologist and a public health person will both understand the strengths and limitations because everyone's understood the model, right? It's known to be not correct, but there are known facets of it that are useful to discuss, like reproduction numbers can emerge from these things, R numbers, things like that, right? And then so we can use those concepts elsewhere. But once the model has got so complex that it can only be run in a computer, then how do we interpret that when none of us can see or conceive of it? I think it's a major challenge of our time. And we're certainly not going to fully equip you with all the tools you need, but a lot of what this course is about is teaching you how to use tools to deal with that. So what I sort of thought, it's interesting because when I was first thinking about this lecture, which first gave 5 years ago, I'd actually met Steve Wolfram a few times and talked to him a few times, but I didn't know until relatively recently how much of his thinking in this book he has, A New Kind of Science, is similar to the things I'm saying now. And in fact, I only worked it out because he read something that I wrote and he said, oh, you might be interested in the connections. And so it feels important to sort of so people know who Stephen Wolfram is. Wrote Mathematica, CEO of Mathematica, physicist, whatever. And back in the 1980s, he was very interested in these things called cellular automata. And I'll use this one here. So I'm so excited about these new kit. So let's see if this works. Where have I put that? There. Right. So what's interesting about cellular automata is you have a sort of setup where you have some grid. And Can you see it? Oh, zoom out. There we go. It's that one, isn't it? We did this last time, didn't we? There we go. So you have some grid of cells, and this is the sort of thing that back in the, bear in mind in the 1980s, computers weren't very fast, but this is the sort of thing you could easily do on a desktop computer in the 1980s. And you have some notion of cells being alive, and I've colored that cell black to represent it's alive, and cells being dead, and these dead cells are white. And the notion is that you have sort of time turns. Oh, now I regret not how many 1, 2, 3 that mean that there's some progression, and the progression is based on this is the state at time 1, and then this is the state at time 2. So time is discrete, and the way these things progress is based on a set of rules, and those rules are often based on they could be based on the entire state, but often they're based on, say, a neighborhood. So the neighborhood of this cell here triggers how it might behave in the next one, and let's say that if it's got no neighbors, it disappears, right? So at the next stage, the cell dies, and then that's all the cellular automata does. But what Steve Wolfram did was something that initially looks, less interesting, but he sort of said, well, I want to consider these things for simplicity in one dimension. So you have a situation like that, and then that moves to a situation at the next stage. And as we'll sort of see when he did that, what he thought was, what he noticed is if you constrain the neighbors to just be the actual neighbors in one line, if you want to know what this cell should be doing in the next generation, and it's only dependent on its neighbors and itself, then basically it's only dependent on 8 things, right? Because there's 8 possibilities at this stage: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. That's 8. I did it right. So what's nice about that is that if you have constrained your cellular automata in this way, you only have to specify 8 rules, right? Of course, the whole state of this thing is binary. It's very, very large, but we're only looking at the state of neighbors to predict what's going on in the next one. And of course, the same thing will happen here. You look at its neighbors. And now, what's nice about this is Wolfram realized is that if you're dictating what this state here is going to be, the same cell at next time, by a binary value, it's gone off here. That's all right. Then you can specify the entire state of this system by just specifying what that should be for each of these cases. So, you might specify 0, 1, 0, 1, 1, 0, 1, 0. And that defines all the rules you need for this system. Does that make sense? People get that? So this is a cellular automata. And the interesting point about that is, what is that here? An 8-bit number, right? So once you've defined this, you can define every single rule, every single thing that can happen in the laws of this universe. It's a very simple universe. You can define them in one 8-bit number. So how many different possible laws are there in this universe? 256, well, 256, yeah. And what might we want to call this rule? If we're going to number them? Yeah, 0, rule 0. And so what Wolfram did in the 1980s, because computers were powerful enough to do this simulation back then, is he looked at he looked at all the rules, and he exhaustively looked at them, and he found particularly, let's try and get this right, what number am I doing? That's so that's 1, 2, 4, so that's 6, 14, 30. Yeah, I've got it right, have I? Is that 30? Rule 30. So rule 30. So what he's saying is basically, if at this stage, if the center one is 1 like this, then you move on. So in this circumstance, you do get something in there. But then the question, what happens for this cell? So this cell is basically seeing 1, 0, 0. So that is also 1. And what happens for this cell? Well, this cell is seeing 1, 0, 0. So that's also 1. Does that make sense? But then if we go to the next level, we can do the same thing again. But I don't have to go here. I didn't have to go beyond these 3 cells. But here I'm going to have to go, and that one's going to be colored in because it's this rule. This one here, hold on a minute, 1, 1, 0, 0. So that's not got any entry. This one here is also going to be, that's 1, 1, 1. So that's also 0 here. This one here is going to be colored in. That one there is going to be colored in. And we can keep progressing that. Does that make sense? And then, so he actually draws these things. He had papers with these things. It's easy to do graphically as well. You can remember what great work to do in the 1980s. Did you ever implement these things? This is something you would have done. Yeah. This is like, I'm giving, this is like our childhoods. I never was sophisticated enough to implement these things, but Carl-Henrik did. So that's rule 30. So what you get is these rules. Of this form. So this would be rule 1. I've done it the opposite way up to the way I drew it on the board there, but the same idea. Rule 1 is a different type of rule. And he sort of exhaustively went through all these rules. So I've just sort of put up there what I've been describing. This is rule 1, which we didn't talk about. And then this is rule 30, which we did talk about. Okay, so you get this sort of patterns here of what's going on in these cellular automata. Now, if you run that forward, this is the sort of diagram then the Wolfram put in his paper in the 1980s of Rule 30, and he did this exhaustively for all the rules. In fact, you can go and read his blog posts about it. He's got lots of blog posts today about this. So what do we notice? Why have we chosen Rule 30 in terms of the way it's looking? I'm just checking that I did the first stage right. Yeah. Oh, yeah. Nice. I did do it right. So what I drew on the board there was the first 3 stages. This is getting the computer to carry out. Why was Wolfram excited by this rule? And still is excited. He considers it one of the most, in fact, his whole book, A New Kind of Science, is kind of stimulated by this discovery. What's interesting about it? What's the periodicity of this thing? Let's maybe have a look at, let's go to his blog post. And let's look at all the rules. So, oh no, I know what to do. Okay, so, well, first of all, I have to ask you a question. Why is this rule significant for Cambridge? To do with railways? Anyone been to Cambridge North Station? Cambridge North is in the north. Yeah, it's near the industrial park. The whole of Cambridge North Station is decorated in aluminium cladding with Rule 30 imprinted on it. I'll show a picture of that in a minute. So I was going to sort of like, let me just look up. Because actually, oh my gosh, it's covered in Rule 30. So it's a blog post from Stephen Wolfram. So there's Cambridge North Station. And it's actually, it's all rotated and it's a section because it's making it arty, right? You know, so there has to be some subjectiveness in there. And so here's him going through the different rules. And here's him exploring all the rules. So this is all 256 possible cellular automata that come from these rules. So some of them are like, someone like, some of them have these interesting little patterns, a bit of a fractal thing going on. Why has he chosen Rule 30 as the one that interests him? What do you think? Why is that an interesting one? Go ahead, yeah.
You just asked the period, but there isn't a period, is there?
There is no period, yeah. Or if there is, you know, I don't know if there's a period. I don't know if you can prove that there's a period, but it's like pi.
Yeah.
Yeah. What's pi a really good, you know, if you could have access to all the digits of pi, I believe it would be a really good approximation to what? If I could give you a sequence of pi's digits, what would it, I think it's, I don't know, actually, I have to be a bit careful, but my suspicion is it's indistinguishable from, under a number of tests, from, if I don't tell you where I'm starting in the sequence and I just start giving you sequences, what will you think I've generated those numbers from? Looks random, doesn't it? So pseudo-random, actually. So is it true for pi?
Yeah, it's a whole number, right? So it has the frequency of every digit is uniform.
Yeah. So it's even uniform random, yeah.
Yeah, it's a uniform random. Really weird.
In some versions of Mathematica, apparently early versions, I suspect there's good reasons not to use it, because what tends to happen with when you have these pseudo, they do sometimes have a periodicity. Yeah. Yeah. I think if you start.
Yeah. There's a pi system. Yeah. Which has every number existing.
And I think these things are quite difficult to prove. So they're often by observation. But so the observation here is if you go down the central pixel, that the central pixel looks like pretty random states. It's certainly difficult to predict. And what's extraordinary about that is that rule, pretty damn simple. So what you're seeing is enormous complexity coming from a very simple rule. It's interesting. Here's when I was thinking about the rule. There's something that's interesting about it is it's asymmetric, right? So that and that are different. If it weren't asymmetric, you would get some periodicity. I was trying to sort of think about how you can tell when these rules are going to do something interesting and when they're not. And I'm sure, you know, he's got so many writings on this that are super interesting. And I'm sure he's got some sort of answers on this, but notice that it's not symmetric, right? Okay, so that's rule 30. I should that's wrong. I need to say rule 30 now. So here it is in Cambridge with a train there. Look, that's sweet. So I guess that's Cambridge South direction. It could be Ely though. Anyway, it's really an extraordinary thing. You only don't find it surprising because you didn't live before we had computation.
Okay.
So you've grown up with a knowledge that this happens.
Okay.
But when Wolfram's writing this, this is the whole point, right? This is surprising for people who haven't seen computation. So if you have seen this before, then maybe you don't, if you've been taught in computer science, you don't find this surprising. But this is the whole foundation of theories of chaos that became all exciting, you know, that even in, I don't know if you ever watch Jurassic Park, this piece of water could fall off any direction on my hand. That's chaos. Of course, nowadays it would be an AI scientist talking about deep learning, but it was all the rage for a period to sort of look at these highly complex systems. But the point that, I think Wolfram talks about with this is he has this notion of, which, without having read his stuff, is also something that I think is very important for our course, of computational irreducibility. What he's saying is that, like, you can't tell, there is no route to go from those rules to what this sequence is going to look like without playing it out, right? So this is kind of why computation is such a key thing, right? And this it happens in such simple systems. It happens in Navier-Stokes. It happens in, these complexities happen in models of billiard balls crashing into each other, right? In the simplest system. So that's the simplest gas system you could come up with, right? Now, the reason that we don't perceive it in this room is because it's so uncertain, when it comes to gas balls molecules bumping into each other, that actually we can summarize it just by a couple of statistics. It's super uncertain. The uncertainty is total randomness. But you can get these sort of interesting situations where you basically get this computational reducibility. Now, another one, and this is the example I sort of opened with in previous years, and I think the work predates Wolfram's work, but I kind of just love the simplicity of what Wolfram's doing there and what we can say about a very simple universe with very complex behaviors. It's just in one dimension. But would be people heard of sort of Conway's Game of Life. Yeah, so it's another example of a cellular automata. And what I love about the Game of Life is that Conway himself here, I think in particular, he looks like a cross between sort of a medieval prediction of a godlike figure and who was the character in Jurassic Park, the mad scientist, Dr. something or other, who was played by Richard Attenborough. He looks like a cross between the two. So he just kind of looks, and the interesting, he looks somewhat, he's dressed in white, and he is in effect the god of this world in the same way that Stephen Wolfram is somehow the god of the Rule 30 world, that he's defined the rules of the laws of the universe in which these worlds are going to operate, right? And the interesting thing about these universes is we understand the entire state. So if we think back to Laplace's demon, we have those two main components there for us. There is no uncertainty about the laws of nature in these cases, and there's no uncertainty about the state of nature. We're specifying it completely. Whereas in a lot of the uncertainties we've been talking about so far, if we're doing this in the real world, we'll have a lot of uncertainty about, we might have uncertainty about the laws if it's something in economics, and we will often have uncertainty about the data, even if it's something in climate where we have a good sense. Or one of the examples we've worked on in climate, one example that we've worked on in climate is it turns out there's an enormous amount of uncertainty about how much the ice sheets will melt and how much fresh water will enter the southern oceans. And that has a dramatic effect on future climates. And that uncertainty is to do with the topography of Antarctica and how ice sheets move across that topography, which we can't see because it's covered in ice. But in these cases, none of that uncertainty is here. There's just a set of rules. And the rules in Conway's Game of Life are a bit different. So there's again a concept of neighborhood. And in this case, the neighborhood is the 8 squares around it. But all you do is you count the number of living cells in those 8 squares. And if there's 2 or fewer, then the center cell will die through loneliness. If there's 4 or more, the center cell dies through overcrowding. And if there's precisely 3, a new cell is born. So there's just these sort of very simple rules. So you go from death to life when there's 3. But these simple rules lead to quite complex behaviors. Now here it's occurring in 2D, so I'm just showing the time progression in this way. And what's interesting about this is I think the glider is discovered in 1969 as the first example of things that they call spaceships by a guy called Richard Guy. So it's oscillating according to a period, but the period also leads to movement. Now, from the simple rules of life, it's not obvious that such a thing exists. I mean, you think it might exist, but in fact, Conway was interested in coming up with simple rules that led to complex things again. And then even cooler, there's one of these. Does anyone know what this is called? People who played life. Played with life. So this is called a Gosper glider gun. And I think it's the smallest known set of patterns that can be used for creating these gliders. Now, actually, if gliders collide with each other at the right angle, they extinguish each other. So what does that make you start thinking about what this could be used for?
Yeah, I've seen people with Turing machine logic.
Yeah, so we'll come up with that in a moment. Yeah, precisely. You can start doing logic with it. So what's interesting for me about this is the thing called a loafer. It's a different type of spaceship, and it moves more slowly to the left. And it was only discovered in 2013. So the point being that we know the rules of life. We can set the initial conditions, but you actually might only discover some life form in 2013. And to give you a parallel, right? If I give you Navier-Stokes equations, do you know hurricanes exist? No, you don't. You do, I mean, you do because you've seen hurricanes. What actual thing, what do people care about fundamentally? Do they care about hurricanes or Navier-Stokes equations? Hurricanes. So the world we perceive is a world of like hurricanes, the equivalent of the loafer, the equivalent of these emergent phenomena that require some form of computation. If you can view the physical world as carrying out this computation, I certainly think of it that way, that what's going on around us can be viewed as computation. Like it's just computation on a physical media. Yeah. I haven't read it sufficiently to know, but I think it's a very sensible way of looking at the world in terms of that you can sort of see everything. Well, the irreducibility that he would talk about, Wolfram, is computational irreducibility. And that's clearly what's missing here. And even if we understood, which we can never understand, where all the particles of the universe are at any given time, even if we had all the laws, you still need computation to get the output, right? And the things that you care about are not so much the laws themselves, they're the consequences of those laws as living entities. And those come through these emergent phenomena, which often take quite a lot of computation to get to. So people who haven't seen this, have seen this before, shout out what you're seeing here if you haven't seen it before, when you get it. So this is a game of life. What's going on in this game of life? Yeah, this is called the OTCA megapixel. It's a game of life that is simulating the game of life. So it's simulating a glider in there. And of course, you can do this recursively. So you can just loop that, right? Pretty nice, isn't it? That's pretty cool. And then, as we were sort of saying earlier, there's a really nice introduction. If you want to sort of find out more about this, and I think it's actually what the question that was in Conway's mind at the beginning was, what can these systems do? And it turns out they're Turing complete. So you can, I mean, basically, first of all, they have infinite memory because they're operating on an infinite plane. And then you can use, and this is what you're seeing in here, these are bit streams that are formed of gliders, and the presence or absence of a glider is representing a 1 or a 0. And then you can set up, I don't know exactly what this, but this thing here is probably some gate of some kind, which is like if two arrive at the same time, then they might either extinguish or whatever, or another one will get pushed out, giving you gates, logical gates. And people have been through and established everything you need. And yes, you can build a Turing machine in the game of life. Now, why is that sort of interesting? I mean, it's not a practical way to compute, probably, that we know of at the moment. But it's sort of interesting because you're showing from these very simple rules, you can get a universal computer, which is kind of an extraordinary thought, isn't it? That's the sort of level of complexity, not just these emergence of phenomena. Now, there's lots of things in the world that are like that. So it's not just in the sort of, so even like another example that I think is fun to look at and talk about. Yeah.
I think just saying it's very complex. We also have this huge setup of all the bits in the right place to make machine.
Yeah. But it's from the rules, right? So yes, you have to put the state in, people have put into that, but it's from the rules. I mean, yes, we need to work out the state, and that's what the mission was, to see if you can do that. But from the simple rules, there is a way of producing these phenomena. How you're exploring that space is another thing, like whether I can set up the space to produce that. I tell you what, we know that you can set up spaces to produce things in this way. How do we know that? Well, our best understanding of the rules underpinning the universe is, I mean, they're not super easy to write down in the way we are, but they're much simpler than the type of phenomena we see around us. So you're an example of an emergent phenomena. You are a glider or a loafer existing within one of these spaces, right? Where the state space has managed to explore these things and get to the point where you exist. And you are some kind of computer. Right, but you're probably not the easiest thing to study. That's why we have the whole field of biology. Whereas these packing problems are kind of interesting. You get these weird phenomena, sort of complex phenomena coming out. So this is a packing problem. Is like, how can I pack 9 squares into one larger square optimally? What's the most I can fit in? Sorry, what's the actual, the formulation of the problem is, if I have a unit sort of square and how many can I fit in? What's the maximum I can fit in? And that's a trivial, what's the minimal size of the bounding square that goes around 9, right, is the way of putting it. So these packing problems, you've got 9 input boxes. You want to see what's the smallest box that goes around them and what's the ratio between those two sizes. And there's a whole website that I link in the notes by a guy called Eric Friedman that looks at all these packing problems for different shapes. So that seems obvious. With 9, it's like that. But here's the example with 17. And this is the best known solution. It doesn't come out in some sort of elegant way or predictable way. And finding formulae for this is very, very hard. So even with these very simple problems, and I think some of these, if you go to Eric's site, it's extraordinary because some are proven, and then it's really obscure mathematics to prove these. It's like 2 people that work on it, and they're not famous mathematicians. But most aren't proven. They're just like, we've simulated this, and this is the best known answer so far. So there's some really simple physics in some sense behind this, or physics that we can understand. But the emergent phenomena of the question we're interested in, and in this case, this is a nice one that we'll look at it. We'll come back to it when we do emulation, because the case of this question is one where we're actually sort of looking for a single number to be output, where the single number is what's the ratio of the square on the outside. So in this case, it's 4.675 times greater than the small square, right? There's a whole website of those. Here's another one, packing 10. And this is proven by a guy called Walter Stromquist. So this is provably the best way to pack 10. I think that you can probably move those 2 up and down. There's some, but and the answer here is that the ratio is 3 + 1 over the square root of 2. Now, what's quite interesting about these sort of numbers is if you look at work that's going on in our group by Challenger Mishra, people are sort of, what Challenger's doing is effectively trying to, one way of, I think, seeing that is trying to find patterns in numerical answers and then trying to feed them into conjectures to feed them into proofs. So you might imagine that you might have found this numerically, and then you might have noticed that this is 3 + 1 over square root of 2, and that might give you some clues about how to prove that. What this one is, 4.675, is also an interesting number. I mean, it looks like that there might be some provable way of doing that. So when it comes to the models that we've been looking at so far, Gaussian processes, they are also a type of model. They're a model that assumes that the universe is sort of jointly Gaussian. And the sort of things that you can do with these models, if we wanted to, so Carl Henricks explained how we combine these models with observation. But here's another way we could combine this model with observation. So let's imagine that I want to understand what's going on in the world of Gaussian processes. Well, here I've sampled 100 Gaussian processes, but I think here is, 20 Gaussian processes. And here's 1,000 Gaussian processes. Now, what if I have 3 observations that I see in the real world? So if I have these 3 observations I see in the real world, I see that these are consistent with some proportion of my models. If I throw away everything that is not consistent with them, I end up with these about 10 or so examples that are consistent with that data. Now, this process is actually an example of the Bayesian inference process that Carl Henricks has been sharing with you, right? that what's actually going on is here, I'm running a simulation to produce different Gaussian process universes. I'm running enough sufficient simulations that when I observe data, I can decide which of these simulations are consistent with the data. And I can then get some sort of uncertainty about what sort of Gaussian process might have produced this. But the beautiful thing with a Gaussian process is I can do that analytically. So I can use linear algebra, certainly for small data, gets problematic for large data. I can use linear algebra to sort of make that mean prediction. So, but notice the mean is not very representative of the type of functions. Always be aware of that with Gaussian processes, right? It's a mean prediction. But look at some of these things, they're bending much more than the mean does. In fact, if you go to a region where there's no data, the mean prediction will be flat because they'll on average be 0. But the actual functions themselves will be wiggling all over the place, right? Then the beautiful thing about a Gaussian process is we can do this analytically. For any of these other simulations, we can't. So if we want to sort of be in this world where, like, as the question earlier was referring to, it's not just about the rules, it's about what were the initial conditions or the parameters of the system. So the Gaussian process tells us, is almost in some sense the rules that things are jointly Gaussian. But what is the covariance between them, right? That's a parameter. Or that's defined by a set of parameters. So very often we're interested in what those parameters are, and trying to find those parameters. One way we can imagine doing it is we try all sorts of initial settings of those parameters, and then we reject all settings of those parameters that don't fit with the data we observe. The problem with this is massively computationally intractable, right? It's even doing it with Gaussian processes here. The reason I do this is 3 data points is after you get 4 data points, the probability that you've got a Gaussian process that is fitting all 4 starts to collapse. Like, imagine it would have to land on one of these lines. Like, if it landed here, okay, then we would retain 3 functions. But if it lands, anywhere here, we lose all the functions. Here it retains, so we lose all sense of uncertainty. And the amount of sampling you have to do to cover the space to pick up your data becomes way, way, way too large. So this process that we might like to do, which is to run our simulation and see how our simulation maps back to the data, is just computationally intractable. Now, the universe isn't that Gaussian, but it once was. Does anyone know what that is? We can't answer all the questions. We're going to have to rule the maximum number. Anyone else? It's the cosmic. Yeah, go ahead. Yeah, perfect. And do you know what the name of the telescope that recorded that, or scanned it? It's the Planck telescope, actually. So it's the Planck scan. It's the most recent and accurate measure of the temperature fluctuation associated with the cosmic microwave background, which I think that fluctuation is about, if I remember well, it's order of a millionth of the actual temperature. So what you see is that the temperature at the early universe was some millions of degrees, and these are fluctuations, I think as a fraction of a degree or some order like that. There's details in the notes. And what's amazing about that is the whole point in the Planck scan was to try and find that these fluctuations are non-Gaussian, because the standard model of physics tells us that these are Gaussian. And they're hoping to find, because they know the standard model of physics, so it was hoping a way of disproving the standard model of physics. But unfortunately for the Planck scan, whatever accuracy they were doing it, there's no way of telling it's non-Gaussian. So to our ability to measure, this is a Gaussian process. And it's a Gaussian process with about 6 parameters in its covariance function, something like this. And those parameters include the amount of mass in the universe, the amount of dark matter in the universe. All these fundamental constants of the universe dictate the Gaussian process that forms the cosmic microwave background. And in the notes, you can sample your own universe. So that's a sample of a potential universe that's just derived from a Gaussian process. It's a Gaussian process on polar coordinates, so it's not as simple as the things we've been describing. But then what happened, of course, is the universe we see around us is condensed. So the modern universe is a nonlinear function of that latent variable. So there's some sort of latent variable in the past that dictates that you're here. And that's a very nonlinear function of that original Gaussian form, and that's why you're not Gaussian. I mean, if you were Gaussian, you wouldn't exist, right? Because Gaussians are maximum entropy. You don't have this separation. The condensation into separate information, potentially storing entities, means you can have a brain that is separate from the rest of the universe, and that you can use your intelligence to predict how the universe is going to evolve. If we were jointly Gaussian, we couldn't exist, right? It just wouldn't happen. For an outside observer, the universe would be 100% predictable. But for an inside observer, it's just statistical, like the molecules in this room. 100% predictable to the extent that it was predictable with error bars. So what you see is very much, and actually this whole section of A Brief History of Time talks about Laplace's demon, and actually misrepresents Laplace's demon. So one of the reasons why we're very confused about Laplace's demon is because Stephen Hawking in 1988 didn't have the internet, so he couldn't read the context of Laplace's demon, where it's set up as a straw man. It's really a straw man argument. He says you could never do that. But Hawking, in Brief History of Time, is saying, oh, here's this idea of Laplace's demon, and that's what I'm interested in. If we do discover a theory of everything, it would be the ultimate triumph of human reason, for then we would truly know the mind of God. There's Laplace's demon that we've heard before, right? That's what it's inspired by. And this notion of data plus model in compute goes to prediction. But the whole point is what I refer to as Laplace's gremlin. You don't have the whole data, you don't have the model, you don't have the compute, you have massive uncertainty everywhere, right? I mean, sometimes we might have confidence in the physical rules. We might be in a certain situation, we might be looking at a well-mixed chemical beaker where ordinary differential equations give us a really accurate prediction, right? But many times we're not. Sometimes we can move in the world of cellular automata where we know everything apart from the compute. But normally there's uncertainty in each one of these things. But I really think that computational irreducibility is a fascinating piece of uncertainty that is not often talked about, right? So whether or not we reformulate our entire theories of science around it, you need to think about it more, that it exists, right? And that's why we talk about cellular automata. And of course, Laplace's gremlin is just a few pages later. The curve described by a simple molecule of air is regulated in a manner just as certain as the planetary orbits. The only difference between them is that which comes from our ignorance. But the ignorance can come through chaos, through these systems that have simple rules, and through the right initialization can respond in extremely complicated ways that take a lot of computation to understand. Indeed, can provide universal computers themselves. So that's, I don't know, that's weird. So you're chasing your tail there or something like that in some sort of weird recursive thing. So that's why I like this notion of the gremlin. What does the gremlin come from? Well, originally it was a sort of concept in the Second World War. Well, First World War initially, but became famous in the Second World War as a little animal that explained why your plane kept falling apart. So a little homunculus who was messing with things in your plane. So a way of representing the fact that they were having to rush to build planes. The planes weren't well tested, so they often crashed in practice. And it's a sort of way of allowing people to reconcile that. Now, there's a number of other examples in the notes about how this manifests in the real world. But basically what we end up with is this cycle of what we think of as experiment, analyze, design. So you design an experiment, and then you do the experiment, and then you analyze it, and then you design a new experiment. And that experiment itself can involve a number of possible things, which includes some simulation of the universe, which is your best understanding of the universe. But it could also include machine learning tools to help you understand where that simulation is mismatching. And that's kind of what this course is about. We're teaching you one way of doing that. But if you look at what AI for science is dominated by now, and engineering, it's dominated by this approach of, in this design of experiments, including these simulations, but including machine learning as a tool to understand the simulation, because the simulation itself is riddled with these emergent properties, which, you know, just like the glider or the loafer, you don't see in the original rules. And you want some way of abstracting that because you care about the hurricane. You don't care about the Navier-Stokes when you're answering most questions. You might sometimes care about them, but a lot of questions you care about the hurricane, right? Depends whether you're caring if a plane flies or if your property is going to be damaged. So you get this sort of notion where there's all possible models that could exist. And then there's models that we can do computation on. And then there's mathematically analytical models, of which Gaussian processes are just one type. But they're quite a broad type. So the whole game we're playing here is going to try and use this broad type of models, which have these nice computational statistics, to help diagnose and work with models that are computable. We're not going to go into doubly intractable models in this course. Yeah, go ahead.
It's like one loose spot maybe. Why should we actually then, like, if you're saying that, like, you know, the paradigm shift is towards models that are like I mean, using compute big models which are like not easily understandable by a person, and we care about kind of the hurricane, but then actually the underlying thing, like. Then why do you actually care about the analytical model, like analytical models, and not just like, you know, just like throw compute and like the you know, multi-layer perceptron with billions of parameters? Because
whatever you've built can never fully represent the complexity of the universe around you. So you need to understand the limitations in the computational model. And throwing a load of compute multi-layer perceptron at it to reconstruct it, you may not understand when that multi-layer perceptron is not valid. So they've done that, for example, with GraphCast, where when you are interested in future weather prediction, we've got so much data on that, they've been able to use generative AI to reconstruct what future prediction looks like with much less compute without running through the Navier-Stokes. And that's now state-of-the-art weather prediction. But you could only do that because this is such a well-defined term. I think we have to sort of finish up now. So we'll go back into the rest of this next time. And this is the key thing. You know, we haven't said how we're going to do it, and we'll choose some particular way of doing it. But the key point is that we can use machine learning models to capture the abstract nature of the world that we care about, right? That's the key idea. We use the machine learning model to capture the abstract nature of the world. And then we look at what the machine learning model is telling us, which in the GraphCast case is it going to rain tomorrow? Right? It's not capturing everything that Navier-Stokes could tell us about molecule movement. It's capturing the main bit we care about, the cloud cover, the temperature, and everything else. It's abstracting the world in a way that focuses on what we care about. So it's doing the equivalent of that's the hurricane, right? And we're able to choose to train a machine learning model to do that and say, right, we no longer have to compute the rest of physics because the important bit for the questions we care about is it going to rain? Yeah, does that make sense?
Yeah, like, I'm just like trying. I think like I'm trying to like understand how this like, you know, like again, like where this like analytical models actually fitting into this paradigm shift. Because like, for example,
well, the analytical models, if it's analytical, we don't need to do all this stuff because we can normally look at the results by the results of the model. So in some sense, we're moving into this zone of models where it's no longer analytical. So there's the mathematical analytical models. We're using the analytical model of Gaussian process. That's the technique we're teaching, but there's lots of other things you can do to tell us about models that are just computational, where we don't have analytical results, right? So if we look at I mean, it's the amazing thing about all the work on statistical mechanics is what Boltzmann worked on is the point that yes, we can define the state of this room by its macroscopic properties, its temperature, its pressure, its volume. Those are macroscopic terms, right? But underlying that, you know, just in there's like 10 to the 23 molecules in this bit of my skin here, right? 10 to 23 molecules bouncing around at high speed. If we were to try and analytically follow them all, you know, we would never be able to do that. It's computationally beyond anything. But actually, from our perspective, we don't care. Because it's so random that the abstract representation is just pressure, temperature, volume. And that's all you need to know to capture this room. But this room is at maximum entropy. That's the air molecules in this air are at maximum entropy, right? So they're as uncertain as they can be. Many of the systems we care about have some degree of uncertainty and some degree of determinism. And it's that combination that we're trying to understand, right? Because a hurricane isn't at maximum uncertainty. So we can abstract this room with 3 parameters, but we can't abstract a hurricane or predict a hurricane with just those 3 parameters. I mean, actually, if you look at the Navier-Stokes, they're abstracting the cells in that way, right? At some very fine level. But we need to do a bunch of computation to turn that into something interpretable. But once we've done that computation, what people have now shown is I can throw all that into a big neural network and I can reproduce what the results of that computation would be without rerunning that computation. And that's at the heart of what this course is teaching about and has been doing for 5 years. So we were very fast seeing in terms of this was going to be the dominant approach in terms of how we start solving physical models. Last question, because I think we're overrunning it.
But this seems like a VLAN, but we can solve the equations better than the actual physics, like rather than find a difference on like we just get it.
No, it's not a free lunch at all. It's what's going on is that in the we're not solving better than, we're solving what the Navier-Stokes, we're reconstructing what the Navier-Stokes would be, but to run the Navier-Stokes at that fine-grained level is computationally too intensive. It learns the regularity there is always regularity in these things. So in the example of, in this example, I chose an example where there's very little regularity to sort of show you how bad things can be, right? So that's why Conway is interested in this, because the regularity is extremely hard. There's computational irreducibility here. But if the actual rules you were looking at was some combination of something phenomenal like this, plus some underlying physics, which was predictable, like a parabolic trajectory, which is actually, you know, if I throw this pen at you, that's actually what we have, is some regularity plus some uncertainty, right? In those circumstances, then we can capture the regularity and perhaps express what the uncertainty should be by just looking at multiple previous computational runs. And then you're basically storing up, you're saving the computation you've done before. And if you think about it, this is how your brain works, right? Although the simulation you're studying is not simulation, it's the real world. You don't run around doing everything from first principles. You use your experience of things that worked in the past and your ability to intervene, to learn properties and abstract notions like that's a ball or that's a pen. And this is because the world is filled with conditional independence structure that you can unpick to make predictions. If it weren't, we would be back where? This is basically a world without conditional independence in structure, right? There is some, you know, all you can sort of tell is it's jointly Gaussian, right? So if I know something about the speed of the molecule over here, if I know the temperature, pressure, and volume of the room, right, that tells me nothing about the speed of a molecule here. If I don't know the temperature, pressure, volume of the room, that tells me something about the temperature, pressure. Actually, I guess it's just temperature I care about in this case. Then the temperature tells me something about the temperature, which would tell me something about the molecule here. But if I know something, but if I know the parameters of this universe, right, basically, I don't learn anything in this sort of unstructured thing. So what you actually need in practice to start making these predictions, sorry, we're overrunning, so do feel free to click off, is conditional independent structure in these probability distributions that allow you to make these predictions. And that's what we have around us. I mean, this object is conditionally independent in some way from the table, right? Which I think of as one object, because if I move it, all the molecules move together. There's a dependent structure within it that is driven by, I don't know, what is it? Strong molecular force or electromagnetic something or other, some physics thing that basically means that thing wasn't attached, whereas these other things are attached, right? And these forces are giving these structures in the world that give the world structure and make it predictable at the macroscopic level, right? Either they're happening down at the microscopic where those laws are, but then they lead to things that we can say at the macroscopic world, the regularities of the universe, but they're difficult to capture sometimes mathematically. Where they are easy to capture mathematically, we call that physics. Where they're difficult to capture mathematically, we call that in increasing order chemistry, biology, social science, yeah, because that's just going deeper into the consequences of these things being run for an enormous amount of time. Yeah, does that make sense? It's fun, isn't it? Okay, right, we'll stop there and see you on Tuesday.